Hi, I'm Alan, and I work at Amazon. I joined Elasticache 6.5 years ago now. In the last couple of years, I've been leading the Amazon's work on the search module. And let me introduce here.
My name is Yair, and I've been working on Valkey search from the very beginning. I work for Google, part of Memory Store.
So we thought we'd spend a few minutes and introduce the search module to people. Recently, there was a new release of the search module with a lot of additional functionality in it, and we're going to talk over that. I'll spend a few minutes and give you an overview, and then I'm going to hand the mic over to Yair, and he's going to run us through some use cases and some of the internals and that kind of good stuff. So I think a lot of people haven't been exposed to the search module before, so I thought I'd give a sort of a very high-level view of what search does in the Valkey context. So what it does is it allows you to create indexes over your existing data. So when you go to the search module and you say, create me an index, it by itself doesn't do anything. You have to put your data into the index. Now, you don't have special commands for that. In the context of the Valkey search, your data lives where it always did. It lives in hash keys, it lives in JSON keys. And you tell the module to create an index over those keys, and the index just sort of automatically populates. So if you change key, then the contents of that key become immediately searchable. You don't need to execute another command. Okay, so essentially it's kind of a fire and forget thing. You set up the index, typically administratively. What I mean by that is maybe once when you create your system, where indexes can come and go. Some people, like for example, in say a session store application, they might create an index for each person that signs on. So as part of the sign-on procedure, they would create an index, data gets loaded into it, and at that point, you're not really paying much attention to that on the ingestion side, okay? On the query side, we have a pretty sophisticated query language that lets you extract keys out of the index, and then you can take those keys that you've located through the searching procedure, and you sort of have an option, which is you can say, look, okay, now that you've found these keys that match this criteria, please give me back the key and maybe some of the fields or all of the fields in the key. But we also have an aggregations module which can take that data and then do some server-side processing on it. And we're going to walk you through some of the examples of that to give you a much better view of what's going on there. Okay. Now, the thing is that the Redis ecosystem has a search module, Redis Search, and the Valkey search module uses pretty much the same commands, pretty much the same query language. So I called that a work-alike. The code base is completely separate. There's no Redis code in there at all, so there's no licensing issues for that for anybody. We've been working along at bringing that functionality to you. There's actually a lot of internal differences on how it works, but if you've been using the Redis search module, you can pretty much port your application over with almost no change to it. That's kind of the goal. And back and forth. All right. So what, conceptually, when you think about a Valkey index, it's really like a table in a relational database. You can almost map the concepts one by one. So you think about a table as a two-dimensional thing. Each row is a key in Valkey, and each column is going to be a piece out of your structured data. So if you're indexing over hash keys, it's going to be a member of that hash. If you're indexing over JSON objects, then you can actually give us a full JSON path, pick out something, and you'll have a column there. And each column has a data type. We'll get in that in a minute. And then the classic SQL operation where you're doing like a select statement, you give it a query expression like a filter, and we go find all of the keys that match that, okay? We don't implement that as filtering under the hood. It is an inverted index, so it's going to have the kind of performance expectations that you would expect from a full inverted index. But logically, you can think about it as a filtering operation. Okay, and as I talked about the aggregation capabilities, you've got things that will do all sorts of processing on your data in aggregate. You can group it, you can aggregate it, you can compute new values, you can bunch them together in all sorts of different ways. Okay. All right, so let's talk about creating an index. So you can have any number of indexes. There's no internal limit on them. In general, you could easily create hundreds or thousands of indexes, and you probably wouldn't notice hardly any performance change in your system with that. You get a little crazy into the hundreds of thousands of indexes, come talk to us. It might not be quite so great, but below that, I think you're going to be fine. Indexes are independent of each other. Queries are executed against an index, but not against other indexes. And that's one of the areas where the query language really diverges from SQL. There's nothing like a table join. Okay, so each table stands alone, or each index stands alone. And we talked about the definitions of the columns, but I didn't really talk about the definitions of the rows. Indexes don't cover every key. You control which keys, ranges of keys, go into the index by providing us with a list of key prefixes. So we went with a prefix rather than a regex expression, frankly, because it's just faster. The internal implementation of that is essentially zero cost. There's a Patricia tree implementation of that. But each index can have a list of key ranges, key prefixes that belong to that, and they're allowed to overlap. And what that means is you can create an index that looks at your data one way, and then you can create a separate index that looks at the same data in a completely different way. Okay? And like I said earlier, you stick a key in and it goes into the indexes automatically. If that key is in 5 indexes, then as soon as that key is accepted and updated, it goes into all 5 indexes. They're all immediately searchable. Okay, there's no delay like you see on some of the other platforms where you ingest the data and seconds later it becomes visible. Okay, consistent with the sort of database semantics, you put it in, it's immediately searchable. Okay, so today, So the search module really has had 3 different versions of it, but 2 major versions. The first version came out last summer, I think it was. Yeah, I think that's right. Last summer. I'm sorry, I don't have the date on the top of my head. And that version had vectors and numeric and tags, and it was really focused around vector search, built off of a code base built by these gentlemen at Google and contributed to Valkey. And in the interim, we've done a lot of work on extending that into the range of full text queries. So now, as we'll look at in a second here, you've really got a considerable addition functionality with that 4th data type. So I talked about text. This is pretty familiar to people that have done text queries. We've got the usual text ingestion processing pipeline. You got punctuation. That'll separate things into words. There's a list that you'd call stop words. If you're not familiar with that, stop words are words to be ignored. Okay, and basically, in English, words like and or the, they happen all the time. They don't help your searches any. They're just a waste of memory. So you can tell the system, don't bother to index those. Okay, those are called stop words. Stemming, again, taking words where we have like suffixes on them, run, running, ran. The stemmer will look at those words and give you the root of those so that you can search for the root and see the different variations. Okay. And you can do prefix and suffix style searching on that. And the vector module has been there for a while. I'm not going to get into too much details. I think Yair might spend some more on that. We talked about, I'm sorry, the gentleman's name escapes me, talked about HNSW as a query. That's in here. So to create an index, it's just a simple command. You list the names of the fields. This is for creating on a hash key. But for example, if you had JSON, you could marry these up with a list of JSON paths. And it just tells the system how to interpret the data that's out there. So a query operation, you give the query string to us. Operationally, we take that query string, we find the keys that are associated with it, we go out to the Valkey database, we fetch the contents of those keys, and either if you're doing a search, it's an early exit, you just get those back, or if you want to do aggregation on them, you use the aggregate command, they go into the processing pipeline, and the results of that get spit out. Okay. So queries are pretty straightforward. You can think about them in a programming language context. They're basically a set of query operators. Each data type has its own operator, and those are connected together with a series of ands and ors. Okay, and I'm not going to go through them, but text has prefix and suffix. You can do phrase matches. You can do what's called what we call a proximity match. This word has to be within so many words of the other word. This is very standard text searching functionality that you've seen on lots of different platforms. Tags are enumerated things that you can do prefix and suffix searches on. Numeric is range queries, just a number, timestamp, counts, anything like that. And then vectors, which of course is a whole separate discussion on its own. Okay, so I'm going to hand it off to Yair to take over.
All right, thank you, Alan. All right, so moving to the third part, I'm going to be discussing two use cases. One is document search, and the second one is semantic search. So starting with the first use case, document search with metadata. So imagine that you would like to implement a very fast capabilities to support searching through articles, and you can specify, your query can specify specific metadata fields like genre, when it was published, the content of the word that appears in the article itself, or the title. So to support this scenario, we're going to be using the following syntax. First, we start with ft_create, specify the index, and we are specifying that the index operates on the hash data type, following on the specification of the attribute or the fields that the hash contain, and which index type each field is each attribute is associated with. Moving on to how do we specify the search? So the syntax, the first query provide you a list of articles that the word noir or detective appear in either the title or the body. You may notice that the query does not specify any attribute, and this is kind of a special syntax, where if the query does not indicate any attribute, the query criteria is considered as a text, where against all the text fields that are associated with the index. The second example show how you can combine multiple attributes or two attributes in the same query. So it extends the first one with an additional filtering, which specifies that we are interested only on articles that their genre has a tag of a thriller. While the robot and uprising appear in either the title or the body itself. The last example is specify a query which combines which filter on genre and its publish a date is after a particular timestamp, which is represented as a variable timestamp, and for numeric fields require start and end. So the start specifies the variable timestamp, while the end uses a special indication, which is plus infinite, which is infinite positive number. Moving on to the second use case. So the second use case is related to semantic search, and in particular, the scenarios that we are discussing is when we are maintaining a product catalog, and the catalog contain a field which is the represent attribute of the product through a vector value. And the first query specify that we are interested to in only the top 5 products that match an input vector. If you examine the query syntax, it's a little bit different than what we have seen earlier. It's comprised of two sections. One of which is the left part, which is a star. Basically, it's the left part specify a filter where the vector operate a filter of the data set that the vector search would operate on. In our case, we are not constraining. Basically, we are looking for all throughout all the records, the products which are matching the given input. The second example is a little bit more complex, but it's incorporate a filter and a vector search. Instead of the star, we are actually constraining the data set that the vector search operate on to the product with the color white, and the price range is up to 100. Beyond searching, we also support FT aggregate. FT aggregate is a very powerful server-side pipelining mechanism. The pipeline comprised of several stages. So every stage, so the first stage is filtering. You specify the filter, apply. You specify what is how do you manipulate the records that matches the filter. You then follow up with a group by and reduction. How do you group? Do you do the group by? Follow up by the how do you sort? You can specify how sorting is being done. In this particular example shown here, it shows how you can craft a query that return all the products which the color is red, and their price band is aligned to 50 to the value of 50. So meaning how many following with how many instances you would like to have. So meaning how many products between the price range of 0 to 50, 50 to 100, which their color is red. Following on the syntax itself, we specify the command index that the aggregation operate on, the filter, which is color red, apply, is a manipulation function. And then we specify the group and a reduction function of count to achieve this. Moving on to the fourth part, which is some in which I'm going to be sharing some details about lower level implementation. Starting off with scalability. It was very important for us, to maintain a very high performance and scalable solution. We have incorporated a couple of mechanisms in order to avoid, to make sure that the read path remain very optimized, in a sense that it doesn't use any lock while processing read commands. So it's lock-free, and we are able to scale pretty linearly the read path. The ingestion path does have a lock involved to update some data types, but it is scalable and it performs. It's also provide very high throughput and low latency as well. Zooming in a little bit to the threading model and how do we achieve lock-free on the read path. So we have incorporated a mechanism that the idea is to time slice the CPU between reads and write. The time slice span over a very short period of time, millisecond or two, the max time span between those between each span of the cycle, and the concurrency level, the concurrency support concurrent reads and concurrent write, but not simultaneously read and write at the same time. And this we implemented this mechanism, and this ensures that there is no contention, basically, through the read path, which is very important for Valkey in general. And we are able to scale very well with this architecture. In terms of consistency, so we follow the read after write consistency, which basically means that read after write consistency on the same connection. It is done through blocking the ingestion or blocking the sending back the reply before the ingestion is completed. And we are also incorporated some special handling for multi-exec. While the consistency level between the replica and the primary remain eventually consistency. In terms of cluster support, it is completely transparent to the user. The user issue the query against either standalone or cluster in the same ways. All the hard all the nuance of handling clusters is done by the receiving node of the query, which can be any node in the cluster, and it is responsible for fanning out, determine which node to fan out to per shard. and then merge the result back and send it back to the user. We encourage you to try it out. It is part of the Docker Valkey bundle, along with JSON and search. Here we specify like where we can find the source. The documentation is part of the official documentation, license as Ellen discussed, and support is the following clients. And contribution is welcome. We encourage everyone to hop in and be part of the active development, influence the roadmap, and so forth. Thank you.